Alright, so turns out I truncated 5.6 a little bit more than I should have. And so there are two remaining examples from 5.6 that we need to go through, because they will show up on your homework and possibly on the AP test. So this will be 5.6 concluded. What are we doing on focus? That'll work. Okay. So the first example is going to deal with continuously compounded interest, which we'll see in a second is actually not a thing. Banks do not offer continuously compounding interest. The best that a bank is going to do is daily. But for any interest formula, what we have is that our future value is going to be whatever your principal is, which is sometimes called the present value, PV, times 1, big 1, plus the advertised interest rate divided by how many times in a given year the interest is calculated, whether it's monthly or weekly or, as we'll see in this problem, daily. And then this whole expression is raised to the n, that amount of compounding periods, times t. And if you remember when we introduced the natural number, we actually saw that with this expression, that as n got bigger and bigger and bigger, you eventually approached a limit, and that limit was e. And so the continuously compounding, so this would be the future value of an amount deposited at rate R, compounded n times yearly. If we wanted to have somehow continuous growth, we found that this actually approached a limit, and so that limit is the PERT formula that you've no doubt seen before, principal times e raised to the RT. So this is continuous compounding. So we're going to do a quick example that compares these two. What we'll see is that continuous compounding provides a pretty decent approximation of daily compounding, and is usually an easier thing with which to deal. So this will be example 5 from 5.6, which is on page 484 if you want to follow along in your book. And we're asked to do a couple things. We're told that there's a bank account that offers 4% annual interest compounded daily. And what we're going to do is first approximate that amount using continuous compounding, and then find the actual amount and convince ourselves that this does a pretty good job approximating this amount. But then we're going to figure out what is the the effective annual interest rate. Because what we saw when we looked at E was the more often you compound, the more interest you earn if you're saving money, or if you're in the unfortunate circumstance where you owe money, the more that you end up owing. And so you actually will earn a slightly higher interest rate than 4% if they're compounding it every day. And so we'll see exactly how much higher than 4% it is. It's not astronomical, but it is something. Okay. So for part A, just kind of list off our parts. Our principal is 1,000. The rate is 4%. And how long are we doing this for? After 1 year. So T is going to be 1. And so the approximation, if we were going to do continuous compounding, would be future value is equal to 1,000 times e raised to the 0.04, and then t is just 1, so leave it at that. And if we bust out our handy dandy TI 84 plus CE, and hope that it has battery because it hasn't been turned on in a while. Oh, happy day. And what we're doing here, ooh, 2 to the square root of 3, that was fun. I don't care about that anymore. Let's do 1,000 times e, there should be an e to the button hidden on the second of your ln, and we want e to the 0.04. And it comes out to be 1,040.810774, which the bank would undoubtedly call $1,040.81. Oh, that's not where that goes. Okay. Doing good today. $1,040.81, which we should see that's higher than 4%, because 4% would have been $40 even. We got an extra 81 cents. Okay, but let's see what the bank actually does, which is use this formula but plugs in 365. Okay, so same principle, same rate, same time, but now we have to account for this n, and daily means 365. So our future value will be 1,000 times 1 plus 0.04 cut into 365 little pieces for each day of the year. And then we do this calculation 365 times. And so in our calculator, we go to enter this in. 1,000 times parentheses 1. Oh, that's not 1, that's a plus. 1 plus 0.04 divided by 365 raised to the 365th power. And you can see, ooh, hello. It is not, no, sorry. It is not the same number. It's not identical to the continuous compounding. You get a little more from continuous compounding, but it's a pretty close approximation, especially if we're going to round to the cent. It ends up being the same in the eyes of the bank. Okay, so this turns out to be 1,040 and 80.8 whatever cents, but effectively the bank will call this the same as the continuous compounding, and so it's a fair approximation. And the final piece is, okay, this is clearly more than 4% that we've earned. So what is the effective interest rate? And so the effective interest rate just means actual we're just going to take the ratio of your future value divided by your starting principal, which for us is 1,040.81 divided by our starting amount of 1,000. Actually, let's just use this guy since it's fresh. So divide that by 1,000, and we get 1 point, let's make sure we can see that, 0.400808, and so this part is the actual interest rate. Okay, we didn't just earn 1.04 back, we earned 1.40808, and so the interest rate is 4.081, let's call it. So not astronomically higher than 4%, but it is something. And if you had a lot of money, you would notice. All right, so that was example 5. We're going to skip example 6 and finish up with example 7, which is a pretty interesting type of problem. It will take a slight bit of development to get to the part where we can actually do it. And I think the book actually does a halfway decent job of introducing it. So they start about midway down on page 486, if you want to flip there now and kind of follow along. And it starts off with suppose. Just suppose that now that a quantity increases at a rate proportional to the difference between a fixed number a and its size. Whoa. Okay. So a quantity increases at a rate. So the rate of increase or the rate of change of a function, we should be thinking derivative all day. And so as the book tells us, this turns into dy dt of some quantity y is changing in such a way that it is proportional. Remember that direct proportion we worked earlier in this lesson means that it's some constant times some other quantity. Well, the quantity that it is proportional to is the difference between a fixed number a, difference meaning subtraction, and its size, it being the quantity itself, being the function, otherwise known as y. Okay? So the derivative of some function y, function of t, is equal to some unknown constant times the difference between another constant and the quantity itself. When in the world would this be something that would govern an actual rate of change? Well, I think it's helpful to see the graph of what y will look like, and that'll help illustrate, and I'll give a couple examples, and then we'll see in a minute that the graph actually makes sense from a calculus standpoint too. But essentially what this essentially what this function is going to model is as you approach a limit, and I mean this in a very normal way, a limit of efficiency, okay, of some task or some goal or what have you. And so the graphical interpretation of what's happening here is that it looks something like, this is a, this is some limit, maybe it's the amount of sweaters we can produce in a day. This would be t. What it says is the derivative, as you get closer to this highest level of efficiency, the derivative decreases. Okay? Your rate of improvement decreases over time, which I think we can all agree sort of stands our own experience that when you first learn something, you tend to make pretty big leaps in improvement. And so if we're kind of tracking the derivative of this curve, we can see at first it's pretty steep. Okay? But then as time goes and we start getting closer to our limit of ability, that rate of improvement or that rate of increase or that rate of change or that derivative starts to level out. So as we get the quantity closer to a, the derivative starts to approach 0. Okay? And that change stops being as dramatic. The example that I think of is with distance running. Okay? If you're a collegiate runner and you run 4:15 as a freshman, and then the next year you run 4:05 in the mile, you might be thinking, oh, I improved 10 seconds in a year, then I should probably break 4 minutes in the mile next year. But what you find is as you get closer to that elite level, to that peak of your own abilities, the improvements start to slow down, which makes sense because the 5 seconds from 4:05 to 4 flat is a lot different than the 5 seconds from 4:10 to 4:05. And that's all that this relationship is saying, is that as you get closer to this limit, whether it's production limit or human limit or whatever, that the rate of improvement, the rate of change, is going to start to stall out. Okay? So the question is, what is this function? What should this function look like? Well, this is a differentiable equation, and we can separate it and integrate and just have all sorts of fun and figure out what the actual function that governs that graph is. Okay, so what we want to do is separate out these differentials and get our y's together. We've got a y here, but let's first separate it. So we'll have dy, oh, this we're all in blue. dy is equal to k times a minus y dt. Remembering that k is just some constant, so it's not going to mess up any integration. We want to get the y with the dy, so we divide it over, and we end up with dy divided by a minus y is equal to k dt. Okay, so we're going to integrate on both sides. On the left side, maybe we can zoom in here a little bit, we're going to need to do a u sub here to get this to work. So we'll let u equal a minus y, which means that du is going to be equal to, well, a is just a constant, so it blows away. The derivative of a negative y is a negative 1 dy. Okay, and so then we'll sub that back in, and we end up with a u for our a minus y. Our dy is actually a negative du. Sub in the negative du for dy. On the right side, this is a simple enough integration because k is just a constant, so really we're just integrating on dt. And so this turns into k times t plus some arbitrary constant. Over here, we end up with the opposite of the natural log of the absolute value of u. And yes, technically we'd have a plus c over here, but we're just going to absorb it all into this c. Because the negatives kind of make me uncomfortable, we're going to shift that on over and end up with the ln of u is equal to the negative k times t. We could call this a negative c at this point, but again, c is arbitrary, c is kind of our all-encompassing thing. It doesn't matter if it's positive or negative, so we'll just keep calling it positive c. Okay, and then at this point we should probably sub back in for u. So this is the natural log of a minus y equals negative kt plus c. But we're trying to get an expression for y, or an equation rather, so we know what the function is. And so we need to somehow free the y. And the way we're going to do that is by raising both sides as the exponent on e. On this side, we get that canceling out action with our inverse functions here. And so we end up with the absolute value of a minus y is equal to e to the negative kt times e to the c. Remember that additive property of exponents. But again, we kind of just keep absorbing this constant into more and more general forms. And so this absolute value of a minus y is just equal to c times e raised to the negative kt. And then what to do about our absolute value? A couple ways we could handle it. We could reason with ourselves that we know that y is always going to be less than a, because we've sort of self-established at the beginning that a is sort of this built-in cap or limit to our quantity. Or if we wanted to, we could do the plus or minus and then just say, well, c can be plus or minus, doesn't matter, let's choose it to be plus. In either case, the absolute values will go away. And we end up with still c times e to the negative kt. And we're almost home free. We'll subtract a from both sides. Get negative a plus c times e raised to the negative kt. But we don't care what the opposite of y is, we want y actually. And so we multiply through a negative 1. We see that the function is going to be a minus c to the e, c times e to the negative kt. Well, okay, that's kind of a funky looking function, but we can handle it. But this is going to be the function that governs any sort of learning curve situation, any sort of approaching a maximum ability or production value or what have you. What we'll see, if we pull this back up to our graph, it actually will confirm what we see here. That knowing that this is governed by a minus c to the times e to the negative kt, I sort of just told you, okay, well, as t approaches infinity, you approach this sort of built-in limit, this built-in capacity of a, but now we can actually show ourselves with calculus. And if we take the limit on both sides as t approaches infinity, what happens to that function as t approaches infinity? Well, this limit don't care about a is just a constant. It certainly does care about this guy though, because t is in there. So this limit turns into, well, let's rearrange a little bit. This will be the limit as t approaches infinity of a minus c over e to the kt, making that negative exponent positive. Okay, and so let's now sub in this infinite t. We get a minus c over e to the infinity. Well, pretty sure e to the infinity is going to be a really, really, really big number. E minus c to the over this really, really big number. Whatever c is, it ain't no match for infinity. This thing is equal to 0. And so we can see from calculus, quite literally, the limit of this function is a. It does not reach a higher value than a. And calculus has sort of given us that ability. So, with all of that lead up, we are then going to now look at example 7, which will be looking at the daily production of a worker in a factory and what is going on as he approaches sort of the cap or the max efficiency level. Okay, so I want to maybe flip to a new page. Oh wow, we have reached the last page in Mr. Smith's notebook. That is a momentous occasion. Okay, so example 7. reads as follows. A new employee performs a job more efficiently each day in such a way that if y units are produced per day after t days on the job, then the rate of change of y with respect to t is equal to k times 80 minus y. K times 80 minus y. So the derivative, the rate of change of how a new employee is performing their job is equal to k times 80 minus y. Okay, so 80 is the A. 80 is the limit. This is the maximum amount that an employee is going to be expected to produce in a day. Okay, and so because its derivative is governed by this relationship, looks pretty familiar, right? Looks pretty familiar. We know that we can use this rule for the function. Okay, so we'll go straight to that part. I don't have to go through all those steps again. We know that the amount of items that a worker can produce will be governed by this expression here, this equation here, this A value minus some constant, which we'll call B for just to be consistent with the book, times E raised to the negative KT. Okay, and so there's actually two constants that we need to figure out before we can start actually figuring specific daily outputs. We need to figure out what this B value is, and also what the constant of proportionality is. Okay, luckily they give us a handful of initial conditions with which to do that. And so if we want to go off to the side and make our TY chart, we need to be a little careful here. So the rate of improvement is based at the end of each day. So after T days means, okay, after the first day of work, that would be the second day of work, they're going to be at this level. So it tells us that the employee produces 20 units on the first day of work, and this is actually T of 0, because this is after no days on the job. He showed up, he did 20. Okay, the second day would be T1. So that's a little bit of a sticky thing to wrap your head around, but the initial value is 20. That without having any training or any experience, he just did 20 items. Okay, so then the other initial condition is after 10 days, he produced 50. And what we're trying to figure out is how many items should we expect this dude to produce after 30 and 60 days. Well, we need the plug and chug version of our function to be able to get these two values, but these initial conditions will help us get there. So let's start with the very initial one and solve for B. That we know that when y is equal to 20, that means that t is 0. I said that a little bit backwards, but it doesn't really matter. So negative k, whatever it is, times 0 is 0. And so e to the 0 is just 1. And so 20 is equal to, sorry about that, little brain fart, is equal to 80 minus b. This all just blasts to 1. When we subtract the 80, we get negative 60, but we've got the negative out front, and so b is equal to 60. Okay, so one of our constants knocked out, and so now we're looking at a slightly nicer version that y is equal to 80 minus 60 times e raised to the negative kt. So then we use our second initial condition to solve for k, namely that after 10 days, plugging in 10 for t, this guy has done 50 units. And so this should be enough to get us what k is. Negative 30 is equal to negative 60 to the negative 10k. Throw a negative across the whole thing and say that positive 60 times e raised to the negative 10k is equal to positive 30. And so e raised to the negative 10k is equal to 0.5. We'll natural log both sides to get our k down. End up with, color do I want? Let's go blue still. That negative 10k is equal to the ln of 0.5, or that k is equal to the, oh, that should be a, sorry about that, or that k is equal to the ln of 0.5 divided by negative 10. And since it's been a minute, we'll plug that in and do our little rearrangement to make it look nice, so that y is equal to 80 minus 60 times e raised to the, this whole mess, but we know that that's going to kind of blow out, and so we get y equals 80 minus 60 times 0.5 raised to the negative t over 10. Bear with me for uno minuto. I'm not sure this negative should be here. Where did I screw up? I feel like this is usually where somebody would call out from the peanut gallery and tell me, why does this negative still live? Well, we're just going to roll with it, see what happens. If we get into a sticky situation, we'll back up. Okay? That actually looks okay to me. So let's see how this function does with a value of 30, for example. So, I'll call this part C, let's say. After 30 days, what does our function with our worrisome negative sign tell us our output should be? Should be 80 minus 60 to the 0.5 raised to the negative 3. Which, let's see what our calculator does with that. 80 minus 60 times 0.5 raised to the negative 3. Yeah, that ain't right. About 80 minus 60 times 0.5 raised to the positive 3. That is right. So, that negative definitely should not be there. But I am struggling to see why. But we're just going to roll with it for now because this is distant learning, and that's what we do. So this should be 72 and a half. So after 30 days, he's pretty close to that 80 maximum, but not quite there. How about after 60 days, which we'll call part D? Which is 80 minus 60 times 0.5 to the 6th, which comes out to 79.06. So still not quite to that maximum amount. Probably got to give it a few more weeks until he's cranking out 80. All right, that's all I got. Sorry about the speed bump at the end, but hopefully it's good enough to do your homework with later.